Flying solo today? You don't have any backup today? It's just you?
No, it's just me. The others are out somewhere right now.
What's that?
Oh, this works.
There we go. Okay, cool. Thanks. Yeah,
so
that's
try to
great.
pin that to you somewhere and then that pin to you. Yeah, one's in New York, one's in Miami, and I'm still here in Baltimore.
Oh, really? Shit. There we go. All right. Cool. Okay, why don't we get started? This is kind of loud. Can you turn this down a little bit? I feel like, or maybe I'll just put it lower. That's what I'll do. I'll lower it. Yeah, I'm good. So last, I talked to you guys about neuroimaging. And so what I thought I'd do this class is tell you guys about a study, or a set of studies that we did in my lab that uses neuroimaging and some computational modeling to kind of give you an idea of how these techniques are used and some interesting things, interesting questions you can answer with them. So as I said before, my lab is interested in understanding how incentives influence performance. And one facet of that we looked at recently is how large incentives can sometimes lead to this paradoxical case of poor performance or choking under pressure. So to give an idea or an example of this, we can look at this video. This is actually Roberto Baggio in the 1994 World Cup. At the time, he was the best footballer, supposedly the best footballer in the world. And he was playing for Italy, and Italy was playing Brazil in the final game of the World Cup. And if he scores his penalty kick, they would win the World Cup. So let's see how he did. He's taken these kicks thousands upon thousands of times. So he has a great ponytail. That's the first thing to note. But also, he couldn't even put it on the net, right? So he's taken this kick thousands upon thousands of times, but something happens in his brain that causes him to choke under pressure and not even perform the skilled motor task with which that he's been, trying to master his entire life. So why is it that this happened? And this is a fun example, but you can also think about cases in which you choke under pressure in sort of your daily life, maybe on the first exam, right? Or or when you're performing in front of people, like when I'm talking in front of you guys. So in my lab, we're trying to understand why is it that there are these cases when incentives can get really big that you might choke under pressure. And it should be noted that in economics, the thinking is that increasing incentives, so if you see here, will sort of lead to increasing performance up until a certain point, and then people will asymptote. So the thinking that economists have is that people are rational. You just pay them more and more, they're going to get better and better up until the maximum of their ability, okay? And so basically the idea is that increasing incentives lead to increases in effort and motivation, which lead to increases in performance, right? But what's been found in the field by some behavioral economists is that if incentives increase, you get better only up until a point, sort of this medium range, and then for higher incentives, you tend to choke under pressure. So basically, increasing incentives increase effort and motivation, and sometimes it can get you to do better, and other times it can get you to do worse. And so the experiments that were done to do this, to come up with this finding, economists actually went to India, where they could afford to pay people percentages of their yearly salary to do different tasks. And what they found was that in these real world settings, if you pay people to do these tasks and you pay them a lot of money, they tend to choke under pressure. But they didn't really come up with sort of a neuroscientific reason as to why this happens, okay? What was suggested by them and by others in psychology is this idea of overmotivation. So basically, the incentive makes you overmotivated, whatever that means, and that's what gets you to choke under pressure. But basically, there's a poor neuroscientific understanding of skilled task performance for incentives. We don't really know what that overmotivation is and why it gets Roberto Baggio to choke under pressure or other people to choke under pressure when they're doing certain tasks. And that's what we're trying to figure out. And one region of the brain that we thought could be involved in this is this area in blue here that's sort of deep in the middle of your brain called the ventral striatum, which is made up of the nucleus accumbens and the ventral parts of putamen. So this area has been shown to encode reward values. So if I just show you a reward and show you increasing rewards, ventral striatal activity tends to increase with increasing reward value. What's also been found is that this area sort of mediates motivated responding for incentives. So if I tell you to do something for a certain incentive, this area tends to light up and is related to both your motor performance and the incentives that are offered to you. Okay, so we thought that this could be an area that could be responsible for that choking under pressure phenomenon. So I said before, ventral striatum encodes rewards and punishments. It's involved with regulating instrumental motor responses, so how you just sort of make simple motor responses to approach or avoid different things, and it mediates the effects of rewards on increases in motor performance. So if I offer you an incentive to do something, ventral striatum encodes both the action that you're taking and the value of that action, or the value associated with that action. So what we wanted to ask was, what are the neural mechanisms underlying paradoxical performance for incentives? And the way we did that is we wanted to create a task that was novel to subjects and that could be standardized in terms of its difficulty across participants. So we wanted to bring people in, have them do a skilled task that was novel to them so that everybody could sort of start on an even playing field. And then we could look at how variance in their performance for incentives was how their performance varied with those incentives when they were sort of standardized at that difficulty level. So to do this, we put people in an MRI scanner. So that's what this is here, a huge magnet essentially. And we scanned their, and we tracked their hand movements with some motion tracking cameras. So these cameras allowed us to attach a sensor onto their hand, and then we could sort of visualize how they moved in the scanner. So we had people making reaching movements in the scanner, track their hands while they were doing a task that consisted of controlling a spring mass system. So basically what they saw was a hand cursor, which is here in white. So as they moved their hand, this white cursor would move. And it was attached to a mass, a virtual mass, in yellow, via a spring. So as they moved their hand, this mass would oscillate back and forth. And their job was to get both of these cursors into this target area. Okay, and the reason we chose this task was because it was completely novel to participants. It has a completely foreign set of physics to them, so we could basically teach them to do this task, have them learn it, and everybody sort of starts at the same difficulty level, right? And then we could standardize that difficulty level and figure out how their performance varies with incentive from that difficulty level. Okay? Does anybody have any questions so far? And so on the first day of the experiment, what they do is they'd come in and they'd put both of these, they'd have 2 seconds to do the motor task, and they'd basically be told, you know, you want to put both of these cursors into this target area, okay? And they did this over 500 trials. So they had a lot of trials to learn and get really good at it. Here there are no incentives involved. It's just to get them good at the task. And so what you see here is performance before learning. You can see they're really bad. So their job was to put both of those cursors into the target, but it's very challenging when they're first starting off. After learning, you can see that they're able to sort of skillfully put both of those cursors into the target. Okay, so they get really good at it over the course of learning. And so what you see here is data from that training phase. So, So as trial number increase, you see performance here, performance sort of asymptotes, they get really good, and they have this significant improvement in performance after learning. So what we can do is, what we can show is that as you learn more, we can get you really good at the task. But what we're interested in is how you do for incentives. Oh, actually I forgot to mention one thing. We also did a thresholding. So to standardize difficulty, we showed people different sizes of targets and fit a psychometric function so we could figure out where everybody had 60 and 80% success. That way we can have everybody at standardized difficulty levels depending on their performance, okay? So we basically give them varying target sizes, fit a psychometric function, so this is target size on the x-axis, performance on the y-axis, and we choose the hard level as being 60% success, a target that gives you 60% success, and an easy level as one that gives you 80% success. And we can make sure we get those levels specific for each subject because we've done this thresholding, okay? Does that make sense to everybody? And then for the incentivized task itself, what we do is we have them come in the next day and we tell them that they're going to play for money, and trials can vary between $0 and $100. And we tell them we're going to extract one trial and pay you depending on your performance on that single trial. So what they see is the incentive they're playing for, the same task that they've trained on, and the outcome of whether they won or lost. And since we're taking one trial at random, it's in their best interest to do their best on all trials, is the thinking, okay? And so here you see the incentive resulting in peak performance and just the frequency at which that happens. So what you can see is that over the easy and hard difficulty levels, people sort of reach peak incentive over the range of incentives, right? There seems to be a lot of variability in which people reach their maximum performance for a given incentive. And so if we sort of standardize and just look at low, medium, and high incentive levels, so this is low incentive levels, $0 to $5, medium incentive levels, 25, 50, 75, and then high incentive levels, 100. For the easy and hard conditions, people's performance on the y-axis. You can see in the easy case, people have increasing performance for increasing incentives, but then in the hard case, people have increasing performance only up until a point, and then when really high incentives are offered, they tend to choke under pressure. Okay, so that shows that we can replicate this choking phenomenon that's been shown in the field, right? But we wanted to know what's happening in the brain when this choking is happening. Okay, is everybody clear so far on the paradigm and what we were looking at? And so the way we looked at this is we had people in the MRI scanner when they were doing this incentive task. So we're able to take images that allow us to partition the brain into voxels, as you saw last class. We have time courses associated with each one of those voxels. We can create a general linear model then, in which we model the experimental conditions and map the explanation of variance in those experimental conditions onto onto brain activity, okay? And so in our case, the general linear model that we used, so this is the brain data, and we were looking at the time of incentive presentation. When you first saw the incentive, we want to look at how brain activity varies with increasing incentives when you first see the incentive you're playing for, and also how brain activity varies with incentive when you're doing the task itself, both during successful and unsuccessful trials, okay? So this model allows us to say what areas in the brain are positively correlated with brain activity when you're doing the task, or when you're seeing the incentives you're playing for, and when you're actually doing the task. And so our hypothesis to begin with was that the larger a subject's neural sensitivity to incentive, the more they would choke under pressure. So along with this over-motivation idea, we thought, okay, well, over-motivation might mean that, okay, I'm just encoding rewards more steeply or more sharply than others, and those people that encode rewards more sharply are those who choke under pressure. So to look at that hypothesis, we sort of looked at neural activity in the ventral striatum at the time of incentive presentation and at the time of motor task, okay? And so as we expected, if you see incentive here and then just the average level of activity in ventral striatum, you can see that activity in this area increases with increasing incentives, all right? So that sort of goes along with the over-motivation idea. The more incentive you have, the more activity you're going to have in this area. And so a lot of people had shown that before us, and so we thought that could be related to over-motivation. But when people are doing the task, we saw the same area of the brain actually deactivated, right? So as incentives increased, activation in this area actually deactivated. So we saw that, and that looked really weird to us, but we thought, all right, well, we'll just forget about that. This looks like this over-motivation idea, so let's test if that's what's going on here. So to do that, we created a measure of neural sensitivity to incentive where we looked at the slope between incentives and the percent signal change in the ventral striatum. So you can see during incentive presentation, those tended to be positive because activity would increase with increasing incentives when you were presented with an incentive. And during the motor task, they tended to deactivate because we saw that deactivation before. But as I said, initially we were only sort of interested in incentive presentation because it was aligning with what we expected this over-motivation idea to be. So we just looked at a measure of performance at the highest level of incentive, which we thought could be a measure of choking, and neural sensitivity to incentive during incentive presentation. What we found was no relationship. So neural sensitivity to incentive was not related to performance decrements. So it didn't seem like this over-motivation idea was what was happening in the brain. So we looked back at our data and we realized that this activation and deactivation looks a lot like what you get when you present potential gains and potential losses to people. So if I just give you a gamble, once corresponding to potential gain or potential loss, people have shown that ventral striatum activates for potential gains and deactivates for increasing potential losses. So what we thought could be happening is that when you first see the incentive you're playing for, you encode it as a potential gain. When you do the task itself, you might view it as a loss. Okay, and that's why you get these deactivations in ventral striatum. Okay. Now, to give you an idea of how to test this, we wanted to look at this idea of loss aversion. So how you value losses relative to equal magnitude gains. So if what's happening at this time point that I showed you before is that you're encoding potential losses, this deactivation then should be correlated with a measure of how you value losses relative to gains. And the way we test that is we can give you a gamble like this. So what if I told you guys that I was going to flip a coin and one side corresponds to winning an amount of money, the other side corresponds to you having to pay me. And so if I flip this coin, I'll give you $22, and if it comes up heads, and if it comes up tails, you have to pay me 20. How many would actually take that gamble? You guys would take the gamble? So not many people would take the gamble, right? But some of you would, because if you calculate the expected value of this gamble, which is basically just the probability weighted sum of the two options, so there's a 50% chance of heads coming up, and it's $22, 50% chance of tails coming up, it's 20. expected value is 1, right? So chances are that you would actually come out ahead if you took this gamble, but people tend to not take the gamble. It tends to be the case that this win amount needs to be about twice as much as the loss amount for you guys to be willing to take it. So if I were to say to you guys, look, would you want to flip a coin? If it comes up heads, you get 40 bucks, or it comes up tails, I'll pay you, you'll have to pay me 20, you might be more likely to take that gamble, right? And that's because you tend to be loss averse. And that measure of how much you value gains relative to loss is a measure of that loss aversion. So what's been found, and so that actually can be represented here, so with this utility function. So this utility function represents your subjective utility on the y-axis for potential gains and potential losses. So you can see for potential gains of 20, they feel like less of a gain than a loss of 20 feels like that of a loss, right? So your subjective value for negative 20 is a lot more in absolute sense than it is for positive 20. Does that kind of make sense to everybody? And what's interesting is if you give, so in that experiment that I showed you before with these brain regions, ventral striatum lighting up for gains and losses, they basically gave people that exact same coin flip scenario, found that ventral striatum was related to gains and losses, and that actually a measure of your behavioral loss aversion, how much you value losses relative to gains, was predictive of neural activity in this region, right? So it seems to be that ventral striatum actually encodes your level of loss aversion, which relates to our hypothesis about loss aversion taking hold and causing you to choke under pressure, okay? So from these results, we can actually make a couple predictions. One, that ventral striatum deactivation should predict performance decrements. Activity in ventral striatum during the motor task should be related to an individual's loss aversion then. And independent of the neural imaging then, you should be able to predict who's going to choke under pressure depending on how loss averse they are, okay? So we set out to test this with our data. And what you can see here is a test of the first prediction. So this is performance at the $100 incentive level, and then neural sensitivity to incentive at the time of the motor task. What you see is those people that have more deactivations, so negative values here correspond to more deactivations in ventral striatum, tend to choke under pressure the most. So they have lowest performance at the highest level of incentive, right? If you take a measure of behavioral loss aversion from those same subjects and look at neural sensitivity to incentive, those people that are more loss averse tend to deactivate in ventral striatum more during the motor task. And then if you look at behavioral loss aversion versus performance at the $100 incentive level, those people that are more loss averse tend to have worse performance overall, independent of the neural activity by itself. Yeah?
Did you correlate this with socioeconomic status at all? So when $100 would be a more significant fraction of someone's income?
Yeah. So we made sure that everybody was in the same socioeconomic status. Anecdotally, we had somebody come in and do an experiment that claimed to make a six-figure salary. I don't know why they were doing an experiment, but they did not choke under pressure. So like anecdotally, it seems that wealth effects matter. But here to make sure that everybody was controlled over wealth, we sort of made sure that everybody had the same wealth. That's a really good point. Yeah. And so here what we did was, you'll notice there's sort of more data points here. So each of these points correspond to a subject. So we did a follow-up experiment where we basically just replicated this finding with just a pure behavioral study and found that, as I said, that the more deactivation, or the more you choked under pressure, the more loss averse you were. Okay? Does that sort of make sense to everybody? Right, so what we find then is that high incentives lead to this paradoxical case of poor performance, that there's a rapid switching in ventral striatum between incentive presentation and the motor task, and this deactivation of the motor task seems to be related to your loss aversion, and your worries about loss then are what gets you to choke under pressure. And so basically, the idea is a sort of reappraisal hypothesis of how you process incentives. So you first look at the incentive that you're playing for and you think to yourself, all right, I have $100 to win. So I have $100, even though you haven't been given that incentive. But then when you do the task itself, you become worried about the loss of this $100, even though you've never received it. And this incentive reappraisal that's shown in ventral striatum is sort of what gets you to choke under pressure. Your loss or your worries about loss of incentive you never received are what get you to choke under pressure. Okay? Does that sort of make sense to everybody? So one way to test this idea would then be to maybe reframe the task. So this suggests that framing of the task has a big impact on how you perform, right? And one way to frame it would be, for me to reframe it would be to say, instead of playing to win, you're playing to avoid losing. So now if I tell you that you're going to play to avoid losing $100, you might think to yourself, oh no, I have $100 to lose. You do the task and maybe you're cognitively more prepared now. You have less of an incentive reappraisal and you don't choke under pressure. Could be an idea, this could be one hypothesis of incentive reappraisal that could result in performance effects, okay? And so in this framework, we can sort of make predictions about what we think people's performance would look like. So we've tested this domain here, the gain domain, and we know that when people have high loss aversion, they tend to choke under pressure when incentives are very large. But if they're less loss averse, they tend to not choke under pressure, right? So the more loss averse you are, sort of going up in this dimension, the worse you'll do at this task, right? So the reappraisal hypothesis suggests then that actually in the loss domain, you might actually do better for large prospective losses if you're very loss averse, and vice versa for people that are low loss averse, okay? An alternative account, if you're just looking at the strict idea of loss aversion, could be that losses just amp you up even more and you just basically have the same responses just magnified for potential losses. Okay? Does those two hypotheses sort of make sense? Yeah. So we've shown data in these domains, and we've basically shown this choking effect for people that have high loss aversion for prospective gains, and an increase in performance when you have low loss aversion. So we want to ask what's happening for prospective losses. Is it this reappraisal idea or a loss aversion idea? And so the way we did this is we showed people the same sort of setup, except now we had trials, we endowed people with $100 of incentive, and we had trials in which they were playing to avoid losing, and one similar to what we saw before where they were playing to win, right? And again, we would extract one trial and pay them out on that single trial, depending on their performance. So we would initially endow them with that $100, which was theirs to pay any prospective losses, because we couldn't just take money away from people. And then if a gain trial was selected, we would basically pay them if they were successful in those trials. Does that make sense to everybody? And so what we saw was basically, here you see similar to what we saw before, incentives on the x-axis, performance on the y-axis for the low loss aversion subjects and high loss aversion subjects. These are just median split. So for low loss aversion subjects, people have increasing performance for increasing incentive. High loss aversion subjects, performance increases up until a point and then significantly decreases. So that basically just replicates what we found before for potential gains. And then in the loss domain, actually, we find the exact opposite. So low loss aversion subjects tend to choke under pressure for high prospective losses and tend to do better. And people that are high loss averse tend to do better for increasing prospective losses. So high loss aversion subjects choke in the gain frame, low loss aversion subjects choke in the loss frame. Does that sort of make sense? So this reappraisal idea seems to be really what's happening in the behavior itself, right? And so what you can see here is to just look at this on a more continuous scale. You can see behavioral loss aversion on the x-axis, difference in performance on the y-axis between the loss and gain condition. Those people that are more loss averse do better for prospective loss than prospective gain, right? So that just sort of illustrates what we saw in those bar graphs in the previous figure. And so, right, so what we've shown here is the behavioral effects associated with the reappraisal idea. That people that are low loss averse tend to choke more for prospective losses. People that are high loss averse choke more for prospective gains. And again, what we find is that ventral striatum tends to deactivate in the motor task for both conditions, but it deactivates more in the given condition depending on what your loss aversion is. So if we look at difference in performance versus difference in neural sensitivity for losses and gains, those people that do better for prospective loss relative to gain have less deactivation in ventral striatum in the loss condition as compared to the gain condition. And that's actually predicted by loss aversion as well. So those people that are more loss averse tend to deactivate more for for gains relative to losses. Okay? Does anybody have any questions? So it seems that this idea of, oh yeah, go ahead. So yeah, I'm sorry. So yeah, the way we would determine if you're loss averse is we give people the gambles that I mentioned before. So we have people make choices where they're flipping a coin and deciding between whether they want to take that gamble for potential gain or loss. We vary the gain and loss amounts, and for each person then we can find the point at which gains outweigh losses and they're willing to take the gamble. Does that make sense? Yeah. So we're doing that for all of these subjects to classify them as being high or low loss averse. Yeah. Are there any other questions? So we then wanted to ask sort of how things in the ventral striatum are influencing motor performance. And we think that this could happen through functional connectivity between the ventral striatum and the motor cortex related to some interaction between incentives and performance, okay? And we think that a lot of people have shown and suggested that ventral striatum is this general motivational node that integrates both reward and motor ideas. And so we wanted to sort of test if the ventral striatum could be, or the connectivity between ventral striatum and motor cortex could be related to incentive and performance interactions. And so the way we did that is we took a time course of brain activity in the ventral striatum, and we sort of multiplied it by the level of incentive and performance on a given trial. So we did an interaction between the incentives, performance, and ventral striatal activity. And what we found was that this area of premotor cortex activated, okay? And it was actually related to the level of an individual's loss aversion. So those people that were less loss averse actually had more of a, or were more loss averse, had more of a breakdown in connectivity between these two areas in the gain domain as compared to the loss domain. So it seems that when people are choking under pressure, there tends to be a disconnect in value representations in ventral striatum and motor cortical representations, and that's what sort of gives rise to your performance under pressure. And so what we found was that there was this differential behavioral and neural responses for losses and gains. There was a reappraisal during task performance, which seems to motivate behavior for incentives, and that activity in the ventral striatum and its coupling strength with motor cortex influences the degree with which someone chokes. Okay. Does anybody have any questions? Comments? No? Okay. So what this shows us is that fMRI can inform theories of economics. So before, it had always been thought that when you give people incentive, they get better up until a point, or economists always thought, when you give people an incentive, they'll just get better up until a point and then sort of asymptote. And what this suggests actually is that there's this loss aversion effect or loss aversion motivation that sort of comes into play in how you process incentives and how those incentives influence your performance. And these ideas could then be used for incentive mechanism design. So if we know how loss averse you are, we can tailor incentive mechanisms to get certain people to perform well in certain situations that's specifically tailored to each individual. And you can also think now of cognitive strategies that help you sort of reappraise situations to do better in certain scenarios. So we're doing some experiments where we have people sort of think about being in a gain or a loss frame and seeing how this influences whether they perform better or worse depending on how loss averse they are. Okay? So we go back to then Roberto Baggio. What do you think he could do to sort of mitigate choking in this scenario, given what we know to this point? Is there a way that he could reframe the situation to do better? Anybody? No? So I mean, if he were very loss averse, he could sort of think about things. It would actually make sense for him to counterintuitively to think about the possibility of loss, right? Thinking about prospective loss could actually mitigate some of these influences of the corrupting behavior of ventral striatal incentive processing on motor performance. Okay? Yep.
So, something that I find counterintuitive is that if they are choking because of the fact that they're being corrupted as losing rather than gaining, how come when they think of it as losing, they do?
Right. So what we think is it's because that when you prepare so the idea is that you think about, the sooner you think about losses, the more prepared you are for them. Because what we found is that when you see those losses in the loss scenario, you process them, but then when you do the task, your neural activity, when you're actually doing it, is more stable in that same reward area. So it isn't that you're not thinking about losses when you're doing the task. You probably still are. You're just less influenced by them. Yeah. Yeah.
Did you test like people are given like a buffer time period, like in between like?
Yeah. So
Like that kind of regulated out.
Yeah. So we have thought about doing that. So the idea of like, what if I separate the time period with which I present you the incentive versus when you do the task? Will that get you to sort of prepare more, right? So then what that might suggest is that like visualization strategies beforehand could then sort of get you ready and maybe make it so you don't choke under pressure. So we have not tried that, but that's a really good idea. Yeah. So, okay, well that concludes what I had. I just wanted to sort of give you an overview of how to use some of these techniques. If you have any questions now or later, let me know. Thank you.
So what do you think the best answer is?
To not choke on